Hello everyone. In today's class, we will start with the module number 2, PN junctions. So you are familiar with the PN junctions, that is diode or transistor consists of PN junctions. First topic is forward and reverse biased junctions. So one useful feature of a PN junction is that current flows quite freely in the P to N direction when the P region has a positive external voltage relative to N, whereas virtually no current flows when P is made negative relative to N. So as we know, in the forward bias, when the diode or transistor in PN junction, when it is forward biased, the current flows from P to N, and when it is in reverse bias, there is no current flows. So the asymmetry of current flow makes the PN junction diode very useful as a rectifier. So as we know, the diode is used, basic function of a diode is a rectifier, but along with that, biased junctions can also be used as a voltage variable capacitors, photocells, light emitters, and many other electronic devices which are basic to modern electronics. Next, qualitative description of current flow at a junction. So here the figure shows the effect of bias at PN junction. So there are two figures here, and here the continuation of that figure is also here. So all together it is a effect of a bias at a junction. So the transition region width and electric field, electrostatic potential, energy band diagram, and particle flow and current direction within W for equilibrium, that is first one A, equilibrium, that is V equal to 0, and forward bias, that is V is equal to Vf, and reverse bias, that is V is equal to minus Vr, that is shown in the figure. We assume that an applied voltage bias V appears across the transition region of the junction rather than in the neutral N and P regions. So here we are going to assume that whatever the applied voltage bias V, the voltage V, that is going to appear across the transition region of the junction, not in the neutral N and P regions. Obviously there will be some voltage drop or potential drop in the neutral material if a current flows through it. But in most of the PN junction devices, it may be a diode or any other PN junction devices, the length of each region is small as compared with its area, and the doping is usually moderate. So we know that doping is nothing but adding impurities to the semiconductor devices. So doping is either moderate to heavy, thus the resistance is small in each neutral region, and only a small potential drop or very small voltage drop can be maintained outside the space charge region. So for almost all the calculations, it is valid to assume that an applied voltage appears entirely across the transition region. So we shall take voltage V to be positive when the external bias is positive on the P side with respect to the N side. Since an applied voltage changes the electrostatic potential barrier, and therefore the electric field epsilon, that is shown in the figure, electric field within the transition region, we would expect changes in the various components of current at the junction. In addition to this, the separation of energy bands is affected by the applied bias along with the width of the depletion region. So the electrostatic potential barrier at the junction is lowered by forward bias Vf from the equilibrium contact potential V0 to the smaller value V0 minus Vf. So you can observe the energy band diagram here. So this lowering of the potential barrier occurs because a forward bias, that is P is positive with respect to the N. So forward bias rises the electrostatic potential on the P side relative to the N side. For a reverse bias, that is V is equal to minus VR, the opposite occurs. The electrostatic potential of P side is depressed relative to the N side and the potential barrier at the junction becomes larger, that is V0 plus VR. So you can observe that in the figure. So the electric field within the transition region can be deduced from the potential barrier. So we can notice that the field decreases with forward bias since the applied electric field opposes the built-in field. With reverse bias, the field at the junction is increased by the applied field, which is the same direction as the equilibrium field. The change in the electric field at the junction calls for a change in the transition region width W. Since it is still necessary that a proper number of positive and negative charges, that is in the form of uncompensated donor and acceptor atoms, ions, positive and negative charges are going to be exposed for a given value of the electric field. Therefore, we can expect the width W to decrease under forward bias. So that is smaller electric field, then we are going to have a fewer uncompensated charges, and to increase under reverse bias. The separation of the energy bands is a direct function of electrostatic potential barrier at the junction. The height of the electron energy barrier is simply the electronic charge Q times the height of the electrostatic potential barrier. Therefore, the bands are separated less, that is Q times V0 minus Vf. The bands are separated less under forward bias than at equilibrium and more under reverse bias. That is because Q is Q times V0 plus VR. That's why bands under reverse bias are going to be more, separated more. So we assume that Fermi level drop inside each neutral region is essentially the equilibrium value. Therefore, the shifting of energy bands under bias implies a separation of the Fermi level on either side of the junction. So this figure shows the effect of a PN junction. So what all it is showing, that is transition region width and the electric field, electrostatic potential, energy band diagrams that we have seen, and the last one is the particle flow and the current direction within the width W for all the three conditions, that is equilibrium condition, forward bias condition and the reverse bias condition. Thank you for watching the video.